All right, these are solutions to problems about work done by a spring force. So real quickly to summarize, we know that spring force is equal to negative kx. The negative sign here is to indicate that these are opposite in direction. We will never ever have a negative k. The k itself cannot be negative. So if you find yourself plugging positive numbers in for both of these, it's just because you've ignored the fact that they are different in direction. So we could do that often, right? But then you just ignore the negative sign. So that's kind of important. Make sure you don't get twisted up on that. And the the potential energy stored in a spring is 1/2 kx squared, and the work done by a spring is 1/2 kx initial squared minus 1/2 kx final squared. Those are the relationships we're working with here. All right, so number 26. In figure 7.9 is just this, a spring with a block attached to it, and this is its equilibrium position here, right? That's that figure that they refer to often. We must apply a force of magnitude 80 newtons to hold the block stationary at -2, so it'd be like pushing it in, right? So let's see, if it requires a force, we know that spring force is equal to negative kx. So if it requires a force of 80 newtons to hold the spring in when we compress it, in other words, we move it to 2 centimeters, which would be 0.02 meters, then we can solve for k. K would be 80 divided by 0.02, which I think is 4,000 newtons per meter. Let's check that. Right, dividing by 0.02 is the same as multiplying by 50. So 80 divided by 0.02, yeah, 4,000. From that position, we then slowly move the block so that our force does 4 joules of work on the spring block system. And then the block's again stationary. So what's the block's position? So we're going to do 4 joules of work. I'm looking at this equation here. Its initial position, we now know what the K is, newtons per meter. Its initial position is negative 0.02 squared. Notice that that negative sign is going to go away here, minus 1/2 k x final squared. And they suggest in the book that there are going to be 2 answers, and you can see because we're solving for that squared, there will be, in fact, 2 answers. Let's crunch the numbers here. So I'll move this over to the other side, so that gives me 2,000. I'm going to drop my units just for cleaning up the equation. And then here, that's on this side, sorry. I have 2,000 times 0.02 squared. 2,000 times 0.02 squared, that's this expression. So that's on this side, that's negative 0.8, and then I'm going to subtract, something is not right. So that our force, okay, so the trick is here then, if our force is doing 4 joules of work, then the spring force, which is opposed to our force, is doing negative 4 joules of work, right? So in the book, it specifically says our force is doing 4 joules of work. The spring force is acting against us, right? So the spring force will do negative 4 joules of work. So when I found this, this is negative 0.8, and then I'm going to add this, so that will be 3.2 joules of work. So I need to find the square root of 3.2 over 2,000. That's 0.04 plus or minus. So the two positions will be 4 centimeters and negative 4 centimeters. So we were starting from here, x equals negative 2 centimeters. So the answer is telling us that if we continue to push it to 4 centimeters back this way, negative 4 centimeters, we will have done 4 joules of work, and the spring will do negative 4 joules of work. But also if we stretch it back to equilibrium, back to here again, and then to 4. And one way of understanding that is if you think about what the graph of spring force looks like. Spring force versus displacement looks like this, right? It's a straight line. You guys had a straight line like this because we didn't pay attention to the directions, right? If you find the area under this, that's how we find work, from any positive to negative, since it's an odd function, that'll cancel out. So if you go from negative 4 to negative 2, you get the same thing as if you go from negative 4 all the way to 2, because the 2 to negative 2 to 2 part cancels out. Right? That's how we make sense of those two answers there. All right. 27. I'll use the other side of this paper here. A spring and block are in the arrangement of figure 7-9. Again, that's this arrangement where this is the equilibrium position. When the block is pulled out to 4 centimeters, we must apply a force of magnitude 360 newtons to hold it there. That's basically giving us a way of finding K. So it takes a force of 360 newtons to hold it at 4 centimeters. Notice I ditched the negative sign. I know that these are opposite in direction, so that force would have to be negative here. But I know I can't find it. The K cannot be negative. So my spring constant is 360 divided by 0.04. That's 9,000 newtons per meter. That's my K. These problems often happen this way, where there's a little bit of information that lets you find the K in the first place, and you go from there. We must apply a force of magnitude 300. We pull the block to 11 centimeters. So we started at 4 centimeters. Now we're going to pull it out to 11 centimeters, and then release it. How much work does the spring do on the block as the block moves from 5 centimeters to 3 centimeters, and then to negative 3 centimeters, and then to x equals negative 5, and then x equals negative 9. All right, so that's a bunch of different calculations. They're all similar. Work done by a spring is 1/2 K times x initial, which is 0.04 squared. We're releasing it from 11 centimeters, right? Yes, I'm sorry. So it's initially at 11. Right, this whole thing was just to find the K. So it's going to go from 11 to 5 centimeters. Wait a second. Sorry, we're releasing it from 11. I'm sorry, I'm misreading this again. How much work does the spring do on the block as the block moves from 5 centimeters to 3 centimeters? So initially at 5 centimeters, there we go, to 3 centimeters. And if you crunch the numbers there, I have 4,500, I'm factoring that out, times 0.05 squared minus 0.03 squared. That's 7.2 joules. How much work does the spring do when it goes from 5 to negative 0.03? Well, like we talked about, the 3 to negative 0.3, that's actually going to be 0 joules of work. So when you go from 0.05 to negative 0.03, this looks exactly the same. 7.2 joules again. From 5 to negative 5, if we do 5 here and negative 5 here, that's going to be 0 joules, right? And 9 centimeters. So that'll be the same calculation with a from 0.05 to 9 centimeters. Is it -9? It doesn't really matter, right? It could be either one. 9 centimeters is going to be the same. That's going to be negative work, right? And that's going to look like the same calculation we did there, but with a 0.09. Negative 25.2 joules. I'm just going to bring up the answers here real quick. Make sure I'm not leading you astray. And those are all correct. Number 28. During spring semester at MIT, residents of the parallel buildings at East Campus dorm battle on each other with large catapults. We have one in the closet, in fact, just like this kind they're describing. So assume that the stretching of the hose obeys Hooke's law with a spring constant of 100 newtons per meter. If the hose is stretched by 5 meters and then released, how much work does the force from the hose do on the balloon in the pouch by the time the hose reaches its relaxed length? So spring force is equal to 1/2 K times the initial position. It's stretched 5 meters minus 1/2 K, and its final position is when it's at the relaxed length, or in other words, at equilibrium. So it's like 1,250 joules, I think. Yep. And it makes sense that this would be positive because this spring in this case definitely increased the kinetic energy. If we knew the mass of the water balloon, we could actually figure out how fast it would be going, right? Because 1/2 mv squared would have to be equal to this, because work equals change in kinetic energy. Number 29, last one in this set. We have, in the arrangement of figure 7-9 again, we have a block. We gradually pull the block from 0 to +3 centimeters, from here to +3 centimeters. And we have a graph of the work that our force does on the block. So of course the spring force would be opposite to that, right? This is the work done by us. And it looks like this. If you think it looks like a parabola, you would be right, because work done by a spring is 1/2 kx squared, and this is x on this axis, so it is in fact a parabola. And this point right here is the point 3 centimeters, so 0.03 meters, and on this axis this is 0.9 joules. So that means the work done by the spring, which would be the opposite of this, negative 0.9, because they said this is the work done by us pulling it, is equal to 1/2. Do we know the K? I guess we're trying to find the K here. K times the initial position of it is 0 minus 1/2 K. The final position would be at 0.03, right, from here to here. That's what we're doing. And those two negative signs will cancel out, giving me a positive K, which is what we expect. So K would be equal to 0.9 divided by 1/2 times 0.03 squared, which is 2,000. And we want to know now, so the whole purpose of that graph that just got us the K, basically, now it just becomes a repeat of the last problem, or maybe 27, I think 27 it was. How much work does the spring do on the block when the block goes from 5 centimeters to 4 to -2 and to -5? So I'm just going to set up the first one, and you can crank out the rest of them. Right, this is just the same calculation. And this is an odd one, so you have the answers. Tricky thing, I think, was finding the k, figuring out what to do with that graph. So the work done by the spring is equal to 1/2 k x initial. Where are they starting it here? We're starting it at positive 5 centimeters minus 1/2 k, and then final position, the first one is 4 centimeters, and then we're going to do the same calculation with negative 0.02. Of course, it would be the same for positive 0.02. Doesn't make any difference. And then finally at negative 5 centimeters. Right? And when you pop those into your calculating device, you should get that the first one is 0.90 joules. This one is 2.1 joules, and of course 5 to 5 centimeters is 0 joules. Excuse me. There you go. Work done by a spring force.